in the last class, we were looking at how to realize the current controlled voltage source. Ideally, of course, the input resistance must be 0, the output resistance must be 0, and the ratio of the output voltage to the input current must be some resistance R, which is either called the transimpedance or the trans resistance. And the idea is very straightforward. We have an output voltage V naught across load RL, and we want that to be equal to In times R. So, the basic idea, as we discussed yesterday, was to compare this quantity V naught minus In times R with 0 and use negative feedback to go and kick V naught in the right direction. Earlier, in the context of using an op amp, we used a variable voltage source at V naught, but now we recognize that it is also possible to do it with a variable current source, because if you want to increase the potential of a node, you pump in current. If you want to reduce the potential of a node, you drain out current from that node. So, in other words, so basically if V naught minus In times R, that quantity there, is greater than 0, it means that the output voltage is too much or too little? It is too much. So, its voltage must be reduced. So, current must be pulled out of the node V naught. So, in other words, this current here must be proportional to V naught minus In times R, okay, and the constant of proportionality must have a dimensions of conductance, some Gm, and what is the sign of the Gm? Positive, right? And what is the value of Gm you would want ideally? Infinite, right? So, basically this current I is Gm times Vo minus In times R, and ideally Gm must tend to infinity. All right. So, now can you identify the transistor? Very good. So, this is the drain, okay. So if that is the drain, then this must be the source. Great, great. Then where is the gate? So basically, this must be the gate, right? So this is basically Gm times incremental VGS. The gate voltage is V naught minus In times R. Source voltage is 0, and therefore this is the transistor, and we draw it so this is In, that is RL, that is R. Okay. So, what comment can we make about the output resistance? I mean, as Gm tends to infinity, what comment can you make about the input resistance? As Gm tends to infinity, this potential will be 0, and clearly you can see that that's I mean, regardless of the value of In, the voltage at the input of the voltage, I mean current controlled voltage source is 0, right. So regardless of how much current you pull in or push in to the CCVS, the voltage is 0. What does that mean? So it looks like a short circuit. So what is Rin? 0. Okay. All right. What comment can we make about R out? What comment can we make about R out? R out being so there is no point, there is no need to do the math, right. Remember in all our discussion, we said that if Gm tends to infinity, V naught minus In times R is 0, which means where is all the current flowing? That In current, where is it flowing? Pardon? R. So, what is the voltage across R? What is that voltage? In times R. Okay. All right. What is the voltage at the left end of the resistor? 0. So, what is the voltage at the output? The voltage at the output is In times R, and is that dependent on RL? It is not dependent on RL. So, basically this is telling you that here is a voltage source, even if you change the load resistance, the voltage remains the same. So, what comment can we make about the output resistance? Output resistance is 0, and VO by In is R, and as you can see, as Gm tends to infinity, we indeed get the properties of an ideal current controlled voltage source, where the input resistance is 0, the output resistance is 0, and the transimpedance is R, which is again independent of the properties of the transistor itself. All right. And the reason for this is that we are using negative feedback to go and to provide us this transconductance. All right. So, so the next step is to find out what it means to have a high Gm. Okay. And before that, I would like to add a small extension. So, by the way, if you have a poor current source, so let us say this current source is not ideal, then it is equivalent to having a parallel resistance Rs in series in shunt with the current source. All right. And now what comment can we make about the output voltage? The fact that you have finite output resistance for the current source does not change anything as long as Gm is infinite. And why is that? This potential is 0. What comment can you make about that potential? Is yes? U 0. Okay. And therefore, what is the current flowing through Rs? 0. So, Rs does not affect the operation of the circuit at all. So, all the In flows into capital R, and the output voltage will remain In times R. Okay. Now, that basically means that I can now represent this by a Thevenin equivalent. So, that is this is Rs. What does this be? What will that be? Minus In times Rs. All right. And VO, as we saw, is nothing but In times R. Okay. So, if I now call this Vi, what will VO be? Okay. What is the output voltage? Because what is the voltage across Rs? 0. So, no current flows through. This we discussed already, all right, and we are going through the same arguments all over again. Okay. All right. Now, if I convert this into a Thevenin equivalent, how will it look like? This is minus In times Rs. If I call this Vi, what will this be? Correct. It is not because the voltage, the current through through Rs is Vn by Rs. Do you understand? There is a difference between the two. Right? One is the cause and one is the effect. Which is the cause? Okay. All right. So Gm tends to infinity. So the gate voltage is 0. So what is the current flowing in? Minus R by Rs into Vn. Okay, and you didn't have to do any of this stuff, because if minus In times Rs gives you an output voltage of, gives In times R. Now if this is Vn, what will be the output voltage? Vn instead of In, you have to put in minus Vn by Rs, right, times R, without doing any analysis. All right. So now the next thing to do is to figure out what the what happens to the properties of the network when the transconductance is finite. So let's call this Vx. That's Gm times Vx. So what is the current flowing through the resistor? R. That current remains. That current remains In, right, regardless of what happens, because after all In is a current source. So what is the voltage drop across R? In times R. Okay. All right. So now what is the only unknown? Or if you want to solve this network, what will we do? Yeah, you either find Vx or you find Vo. So it doesn't matter. So let's call the Vo is nothing but Vx plus In times R, which is Vo. Okay. And you write which basically is equivalent to saying that this is, if we want to find Vo directly, this voltage is nothing but Vo minus In times R. So we write KCL at the output node. So Gm times Vx, which is nothing but Vo minus In times R plus Vo by RL plus In must be equal to 0. All right. So Vo times Gm plus 1 over RL must be equal to In or minus In times 1 minus Gm R. All right. So Vo over In therefore must be minus, where is R? We forgotten R somewhere. Oh, sorry. Yeah, it's basically GMR minus 1 over 1 plus or Gm plus 1 over R. All right. So which is nothing but, I'll write it in terms of the ideal value R times, how do we write this in a way which is, so this becomes 1 minus sorry, R times Gm minus 1 over R over Gm plus 1 over R. Okay, so what comment can you make? What is considered a large Gm? Sanity check. As Gm tends to infinity, well, the output, the transconductance, trans resistance becomes R, all right. And so, what constitutes a large Gm therefore? What about RL? What constitutes a large Gm? Huh? So, Gm must be much larger than 1 by R and also must be much larger than 1 by R. All right. So, what comment can you make about the output resistance? So, looking in here, what is the output resistance? How will we figure that out? One way of doing it is to simply write the expression for VO by IN when RL tends to infinity. When RL tends to infinity, what is it? Stare at this expression and tell me what it is. As Gm tends to infinity, I mean, sorry, yeah, as RL tends to infinity, what is the output voltage? It's nothing but it just becomes Gm times, it basically becomes R times Gm minus, or this is R times 1 minus 1 over R, okay. And yeah, I guess it's much easier to do it the other way, which is the standard way to do it, which is basically you apply a test voltage and measure the current that's going in. So, we de-energize the source, the input source. This is what we have, and this is Vx. We apply a V test here. What is the I test going? What is the current flowing? What is Vx? V test. Okay, why? No current is flowing through the resistor. Okay, so what is I test therefore? Gm times V test. So, we apply a voltage V test and the current flowing is Gm times V test. So, what is the output resistance? 1 by G. All right. Okay. So, now if the output, if the input current source had a resistance, internal resistance of has an output impedance of Rs, what comment can you make about the output resistance? Think carefully. What is Vx? What is Vx? Rs over Rs plus R times V test. Okay. So, what is I test? V test, very good, V test by R plus Rs into Vx, which is Rs by Rs plus R times V test. So, what is output resistance R out? It is basically Rs plus R by Rs, which is 1 plus R over Rs times 1 over Gm in parallel with, I mean, there is one current flowing like this, there is another current flowing like that. So, it is the parallel combination of two impedances. One is R plus Rs, and that is in parallel with this character. Is that clear? So, what comment can we make about, so therefore, if the current source that is driving the current controlled voltage source has a finite source resistance, right, what comment can you make about the output resistance? Is it higher or is it lower? So, if Rs was infinite, what would be the output resistance? It would be 1 by Gm, right. And by the way, what did we say as what is R in relation to Gm? If you want in a good current control voltage source, what comment can we make about Gm and R? Gm must be much larger than 1 by R. So, what does that intuitively mean? What comment can you make about the current flowing here through the R versus Gm? You are applying a V test here, Gm is very large. So, what comment can you make about this current versus the current flowing through R? Which will be greater? Gm. So, which of these two arms will dominate? Your parallel combination, the path through one, the current through one path is much higher than the current through the other path. So, which path, which term will dominate? The Gm path will dominate. So, what comment can you make if you now put an Rs? What comment can you make about the output resistance? It will increase or decrease?
The other path resistance is increasing again, so it will dominate less.
If this path dominates, what is the output resistance approximately meant?
1 plus R by Rs.
It is 1 plus R by Rs times 1 over Gm. So, the question I am asking you is, if Rs goes from infinity to a finite value, will the output resistance of the amplifier increase or decrease? So, the finite impedance of the current source that is driving the current control voltage source will increase the output resistance, okay. And basically you can see therefore that the Gm must be chosen to be much larger than. So, the bottom line is that Gm must be much larger than 1 over Rs, 1 over RL and 1 over R, okay. Under those circumstances, the output gain will be minus minus I naught times R irrespective of the properties of the transistor. Now, if I remove RL and if I want to find the input resistance, I mean, let us do this quick. What is the input resistance? Very good. R in is 1 over Gm. Okay. And therefore, if the input resistance of the current controlled voltage source is 1 over Gm, you must make sure that the source impedance is much higher than the source you are driving it with, right, has an output resistance of Rs, and the Gm must be made sure, I mean, if you want to make sure that this behaves like a good current controlled voltage source, the input resistance must be much smaller than that of the source. So, the input resistance is 1 over Gm, which must be much smaller than the output resistance of the current source that is driving it. So, Gm must also be much larger than 1 over R. So, if all these three conditions are satisfied, that is what qualifies, that is what it means to say that the Gm is a large Gm. All right. Okay.